Thank you very much for joining us today for our today's class. I'm Mr. Zingapeta and I'll be taking you for fluid mechanics. So the first lecture that we are going to look at is going to be basically on basic concept of fluid mechanics and how to recognize types of fluid flows, fluid flow problems, look at modern engineering problems and how to solve them. And after having that, we also look at how to differentiate between accuracy, precision, and the number of significant figures that you are going to use in engineering calculations. So I understand that most of you have done statics and dynamics, and from statics and dynamics we understand that there are two things that involves around mechanics, which is statics and dynamics. Statics can be defined as the branch of mechanics that deals with bodies at rest, and dynamics, which means this one deals with bodies in motion. So similarly with fluid mechanics, we can divide it also into two categories, which are fluid statics and fluid dynamics. So when it comes to fluid statics, what we have is these are the fluids at rest, and fluid dynamics, which means we are going to have fluids that are in motion. Okay, so the other thing that we can look at is another category of fluid mechanics that we have, although we are not going to look at it much closely in this course. It's known as fluid kinematics. So fluid kinematics is part of fluid dynamics, or it's a branch of fluid mechanics that is almost similar to fluid mechanics. However, the only difference that is there is we don't take into consideration the forces or the pressures that have caused the fluid to move or to be in motion. So if you are going to differentiate between fluid dynamics and fluid kinematics, you can use this simple definition. Fluid dynamics is the study of fluid in motion, considering the forces and pressures that have caused the fluid to gain acceleration or velocity. Whereas fluid kinematics is the study of fluids in motion without considering the forces or pressures that have caused the fluid to gain acceleration or velocity. So that's the major difference that we can look at. Like in fluid dynamics, there is issues of force and pressure that we need to look at. So in fluid dynamics, we can look at different categories that we have under fluid dynamics. Number one is what is known as hydrodynamics, which deals with water, gases, and gases at low speed. But approximately what you're looking at is fluids that are incompressible. So fluids like water, oils that are incompressible, we can take them to be under hydrodynamics. Then the next thing that we look at is hydraulics. So under hydraulics, which means it's a subcategory of hydrodynamics which deals with liquids flow in pipes and open channels. So in the assignment that I gave you, you also need to define what is an open channel. What is an open channel, and how do you differentiate an open channel from flow in pipes? Then the next category that we have again under fluid dynamics is gas dynamics. So under gas dynamics, which means we are dealing with flow of fluids that undergo significant density changes, such as flow of gases through nozzles at high speed. So in this case, which means in other words, we are dealing with fluids which are compressible, so which means density varies with time. Then aerodynamics, this branch is taught also as CBU under mechanical department for the aeronautical engineering students, where we look at flow over bodies, and these bodies are like aircrafts, rockets, even cars at high and low speeds. So we've got high subsonic aerodynamics, and we also have supersonic aerodynamics that we can look at. Then we've got meteorology, oceanology, and hydrology. Those are all types of fluid dynamics that we can look at. So which means one can major in any of these I'm sure even at your workplaces, wherever you are, you can relate to see which field you can major in. But in this course, we are going to look mainly at hydrodynamics, where we are going to look at water or gases that are at low speed. So which means in most of the cases, the flow that we are going to look at is flow which is incompressible flow that we are going to look at. So next question that can come is what is a fluid? How do you define a fluid? So generally we can say a fluid is a substance in liquid or in gaseous state. So a layman can define something, a fluid, in that manner, implying to gases and liquids, something that can flow, we can call it a fluid. However, as an engineer, the way that we define a fluid is as follows. A fluid is a substance that deforms continuously under the influence of a shear stress, no matter how small the shear stress is. So this is how we define a fluid. That is a substance that deforms continuously. So what it means, if you take a look at water in a bucket, when you dip your finger in the water, you see there are some waves that are formed. So which means as long as your finger is in motion, the fluid will continue to deform. So what shows that the fluid is going to deform is waves are formed. Unlike a solid, you can touch a chair, you can touch a table, but you won't see any waves being formed because the force that you're applying on that chair, on that table, it's small, so it cannot deform the fluid or the solid continuously. So that's one of the differences that you can look between solid and liquids. So in other words, we can also define a solid as a solid in terms of stress, where we can say that in solids, stress is proportional to strain. So in this case, we can say sigma is directly proportional to strain. But in fluids, stress is proportional to strain rate. So this is another way of differentiating between a fluid and solid. Okay, so as we look at this picture that we have here, which means when a force is applied in this direction, we are going to have what is known as shear stress, which can be defined as force per unit area. Then we've got what is also known as shear strain, given the symbol alpha, and shear stress, we use the symbol tau. So which means as long as this force is applied, the fluid is going to continuously deform under this force that we have, or under the shear stress, which is equal to force per unit area. Okay, so the other thing that we need to know is to define the terms that we are going to use in this course. The first term that we have is stress. How do we define stress? Stress is defined as force per unit area. So when someone comes home and say that I'm stressed, in other words, they're just telling you that they are force per unit area. So which means that there is a force that is applied at a certain area of a body. So now we have got two main stress definition, or two stress that we have. We have what is known as normal stress and also what is known as shear stress. So for normal stress, if we look at this diagram that we have, we know that when a force is applied on a body at an angle, we can resolve this force into two components if it's a two-dimensional problem that you are looking at. So we've got the tangential force and we've got the normal force that we have here. So for us to define what is known as normal stress, we have to take this normal component of the force and divide by the area. So which means normal stress can be defined as force per unit area, which is the normal force per unit area. Then we've got shear force. In this case, shear force is the tangential force per unit area. So those are the type of stresses that we have. One is defined by sigma and another one is defined by tau. So it leads us to another definition that we need, which is pressure. So pressure can be defined as normal stress. So when someone says that I've got a lot of pressure at work or a lot of pressure at school, which means they're just simply telling you that they've got no more stress. So it's no more stress, the new normal. So then the other thing that we just look at is zero shear stress. So zero shear stress comes in when we've got a fluid which is at rest, and in this case, which means there is no shear stress that is being applied to it. So please take note of these definitions. We'll use them a lot in this course, especially when it comes to calculations. You need to know what you are calculating. I'm sure in high school also you've talked about the other basic differences between liquids and gases, etc. So you can go through this slide on during your spare time, and just to make you remember the things that you did in high school, etc., where we talk about that in a solid the molecules are closely packed. Then in liquids the molecules, they still bombard each other, but they are sparsely packed. Then in gases, the molecules, they move about at random and they are spatially spaced, or they are far apart. Okay, so those are some of the things that we looked at in high school. Then we also need to talk about the applications of fluid mechanics. So there have been some extensive research in artificial hearts that have been done by universities, maybe mainly in America and in other European universities. I don't know here in Africa if we are looking at this, but one another area of interest where we can look at artificial hearts, like for those people that have got heart problem or heart disease, and see how we can apply fluid mechanics in coming up with artificial hearts. So it's one of the applications. Then we've got also natural flows due to weather, and for example Victoria Falls, there rivers that we have, Kafue River, and rain season. Those are some of the application of fluid mechanics that we see naturally. We talk about power plants. We see smoke coming from power plants. It's part of fluid mechanics. We might need to learn and also do some simulation to see how best we can reduce pollution in a town due to power plants that are there. It's another area of interest that we can look at. Boats, design of aircraft, spaceships, cars, even the human body itself. Our bodies are filled with fluids. Every time you wake up in the morning, the first thing that you think of is to run Sunda station or something like that. You take a shower, pipings and all those things. They have to deal with fluids in human body. And piping, we see them every day, piping and plumbing. When you wake up, the first thing that you think of is taking a shower, because of the fluids that we have in the pipes. We are able to also apply fluid mechanics in systems like that. Now, with also issues of renewable energies that are coming into play, we are looking also at wind turbines, so which means we are looking at harnessing the energy from the wind to produce electricity. There's a project that is being done in Serenge where they are trying to come up with some wind turbines to generate some power so as to mitigate the shortages of electricity in Zambia. So all these are some examples of where we can apply fluid mechanics, and I'm sure you know some of the things that you also use at work, like those who are in the mines and those who are working in other different industries. You can relate to some of these applications that we have. So if we take a look at history of fluid mechanics, long time ago people used to use even clay pipes to make sure that they transport either water from one end to another or any type of fluid from one end to another. So it's a branch of mechanics that has been there for a long time ago. We can talk about Osborne Reynolds. We'll come back to Mr. Reynolds when we talk about Reynolds number, which will help us to differentiate between laminar, turbulence, and transitional flows using the Reynolds number. But here he was just doing an experiment to demonstrate turbulence in pipes since a long time ago. Like here it's 1975. I'm sure some of us were not born by this time, 1975, but the branch of mechanics known as fluid mechanics had already existed from as far as the 19th or the 19th century, something like that. So in this case, we take a look also as when brothers, or the Wright brothers, sorry, who came up with an idea of building an aircraft, and for the aircraft to fly, they had to apply the principles of fluid mechanics. So we can see that from as far as we can remember, fluid mechanics has always been there. So now today we're just going to look at the basics of fluid mechanics and talk about one or two assumptions that we need to use in this course to solve problems and do the calculation. The first thing that we need to look at is what is known as non-slip condition. So non-slip condition, we are going to consider that any flow that is going to flow over a surface, we have what is known as non-slip condition, whereby the flow that is close to the surface will be equal to 0. Then as we move away from the surface, like this graph is showing, which means the velocity is going to increase until it reaches the same velocity as the ambient speed of the flow that we have in this case. So it is going to form what is known as a boundary layer, and this boundary layer depends on how viscous the fluid is. So at the end of the day, if we are dealing with an airflow, we've got a point what is known as a point of separation. So a point of separation is a point whereby the flow is separated from the surface where it's flowing on. So in this case, like here, we've got a curved surface, which means the separation flow is when this fluid that we have separates from the surface. So it's known as the separation point. And after the separation point, what we see mostly is a flow which becomes turbulent. And once we've got a turbulent flow, this turbulent flow is a region of low pressure. And the region of low pressure will result in this body being sagged behind and creating a force which is known as drag force. So normally when you're dealing with surfaces, we want to make sure that we avoid separation points so as to have a laminar flow around the surface and keep the body move smoothly without any form of drag on it. Is it drag or drag? Forgive my Zimbabwean accent. Okay, so now when it comes to classification of fluid flows, we will look at number one, which is known as viscous flow, and the other one, which is also known as inviscid flow. So if you are differentiating the two, a viscous flow is when we've got frictional flow that is significant. So which means in this case, we cannot neglect any frictional effects that is there between the fluid and the surface. Then for inviscid flow, in this case, we can neglect the viscous forces. So which means in this case, what we have is mu will be equal to 0, which is the frictional force that is there will be equal to 0. So for viscous flows, friction is significant, and in inviscid flow, friction is negligible. Okay, so if a question comes and you are not given the value of friction forces or anything to do with frictional effects, just look at the terms that are used in the question. If the flow is telling you that is viscous flow, so which means in your calculations, one way or the other, you have to mention issues of frictional effects. But if it's inviscid flow, so which means in your equation, anything that has to do with friction, that term goes to 0. Okay. Then the next thing that we look at is external flow and internal flow. So there is a difference between external flow and internal flow. For external flow, we are looking at flow over surfaces, or the flow that is over an unbounded, or it's an unbounded fluid that we have. So it's the flow of an unbounded fluid over surfaces. So which means flow over a plate, a wire, a pipe, a golf ball, all those things, we call them external flows. So in this case, when you're dealing with external flow, we've got what is known as CD, which is the coefficient of drag. Then for internal flow, we have the flow that is ducted, or the flow that is bounded, the flow inside a pipe or inside a duct. it becomes internal flow. So in this case, we have got CD as well, but the CD that we have is known as coefficient of discharge in most cases. We'll come back to that when we are dealing now with fluid dynamics. So if we look at external flow, we, like what I said before, when we're looking at non-slip conditions, we don't want the flow to separate from the body. So no wonder why you will see when we are dealing with tennis ball or even golf balls, they've got dimples, and tennis balls, they've got a certain shape that they've done to it, so that the flow at least remains attached to the golf ball or the tennis ball, for the tennis ball to move far and faster. So I can ask you a question like, okay, which ball will move faster and further, a smooth ball or a golf ball? So just try to answer that question on your own or with your colleague to find out which ball will move further, a golf ball which has got dimples, or a smooth ball like a snooker ball. So if all condition equal, if I throw a golf ball same size as a snooker ball, which one will go further and faster? Why? Okay, so like what I was explaining before, under non-slip conditions, when you've got flow over a tennis ball like this, it's going to create what is known as the work region. So this work, which is this region behind the tennis ball in this case, is known as the work region, and is a turbulent zone. A turbulent zone that also has low pressure. So low pressure, we know that anything moves from high region of pressure to low region of pressure. So if there's low pressure here, there will be another resulting force that will be created in the opposite direction, which will cause this ball to experience some drag. So that's why I was explaining that we always need our flow to be attached to the surface to reduce drag. Then the next thing that we look at is compressible and incompressible flow. So for compressible and incompressible flow, the major difference is in terms of density. In compressible flow, density is not constant, changes or varies. For compressible flow, density changes during flow. Then incompressible flow, density of the fluid remains constant. So what it means is rho at 1 will be equal to rho at 2. So any term that has got d rho over dt, so change in density over change in time, will go to 0, will be 0 if it's incompressible flow, because rho 1 will be equal to rho 2. So if you subtract rho 1 from rho 2, you get 0. Then for compressible flow, density varies, so which means d rho over dt in this case will not be equal to 0, because rho 1 is not equal to rho 2. So now when you're dealing with flows that are at high speed, like flows over rockets and spacecraft, cars, most of the time, we use what is known as Mach number to define the flow of the speed. So Mach number is equal to speed of the flow divided by the speed of the sound. So if Mach number is equal to 1, we've got a flow that is known as sonic flow. When Mach number is equal to 1, sonic flow. When Mach number is less than 1, we have got subsonic flow. Mach number above 1, supersonic flow. And Mach number greater, way greater than 1 is known as hypersonic flow. So which means any flow that is above, most probably Mach 5, we call it hypersonic flow. So there are a lot of researches that are being done under all these types of Mach numbers that we have. So for sonic flow, there are some aircraft that have been designed for sonic flows for strategic purposes, maybe normally military aircrafts, whereby in this region it's a little bit difficult to control your aircrafts in Mach numbers, Mach number, which is usually known as transonic regime. Then we've got subsonic flow. Subsonic flow, most cars, if not all of them, they move at subsonic flow. And also most passenger aircrafts, they move at subsonic flow. Then supersonic flow, of course, when you talk about supersonic flow, what comes in our mind is military fighter jets. those that move at a speed above speed of sound. That when you hear the sound of the aircraft, by the time you look up there, ndeke, ya kale, there's no ndeke there. It has gone. So, which means when you are hearing the sound, the aircraft is already gone. It's like what they talk about a bullet. A bullet moves at supersonic speed. By the time you hear the sound of the bullet, just know it has missed you. If it hits you, you won't even hear the sound. Maybe you are dead. Then hypersonic flow, there are some aircrafts that are being also developed now to move at these speeds. I remember one aircraft that was under research was moving close to Mach 10, somewhere there, whereby by the time you are hearing the noise, it has gone a long time ago. You can't even allocate it. But in this case, or in our course, we'll mainly concentrate on subsonic flows. Mainly subsonic flows. And subsonic flows, those ones that are less than 0.3. Why 0.3? Because any flow that is less than 0.3 Mach number is incompressible flow. So as we are going to deal with incompressible flows, subsonic, which is Mach number less than 0.3. We can also differentiate the flow in terms of laminar, transitional, and turbulent flow. Okay, so I'm sure we have come across this before. Laminar flow is when you open your tap or your tap at home, you see that if the water is not coming very fast, it comes like one column, which is a laminar flow. But if you increase, if you open the tap for you to have higher velocity coming from the tap, it starts wobbling or moving up and down, showing some transitional flow or even some turbulent flow. Those are some of the examples that I can think of. And if there are people who smoke, you can see that close to the cigarette there, the flow is like one chain. Then away from the cigarette, it's like everyone in the room will start coughing because of the turbulent flow that is as a result of the smoke around the cigarette. So those are some of the examples that we can look at to see the difference between laminar, turbulent, and transitional flow. We'll come back to this when we talk about Reynolds number to differentiate again these three in terms of Reynolds number. Then the next thing that we also want to look at is the difference between natural flow, which is also known as unforced flow, and forced flow. So for natural flow, this is due to buoyancy effects. So flow whereby we know that warm air rises and cooler air is denser, so which means it falls, etc. We have learned about this in geography, if I'm not mistaken, when we're talking about how clouds are formed, that when it's hot, warm air rises, then carries with it with water vapor, all those things, and when it's cool, it comes down, then there's that circulation that is there, which is due to natural flow. Then the next thing that we look at is forced flow. So for forced flow, any flow that we use pump or a fan becomes a forced flow. So if we check like most of the modern houses that are being built these days, they've got tanks that are there, and for you to make sure that you pump water or you take water to the top of the tank, you need a pump. So which means that water becomes, or that flow becomes forced flow. Then sometimes when it's very hot, we use a fan to make sure that we circulate the air around the house. So which means that one becomes a forced flow due to the use of the fan that we have here. Again, steady and unsteady flow. Please take note of all these terms. They are going to be used mainly in this course. So we don't need to come back to these terms again because when a question comes telling you that this is steady flow, this is unsteady flow, you need to know what you are talking about. So for steady flow, it implies that there is no change at any point with time. So the flow that we have, there is no change at any point with time. So which means any term that has got dt in it or change in time will be equal to 0. Will be equal to 0. Then unsteady flow, which means now there is change at a point with time. So we've got change of flow at any point with time. So in other words, any term that is got dt in this case will not be equal to 0 because t1 will not be equal to t2. Okay. So like in this case, picture 1, shows a unsteady flow, and picture 2 at this point it's steady flow that we can see here. So here you can see some region of turbulence here, and at any given point we see that the flow is totally different from at any other point, or at time 1 the flow is different when it's at time 2. But here, picture number B, the flow can be called steady because at any given point you can see that the flow at any given time the flow is the same. Okay, so it's the same when we see a waterfall. Picture A shows unsteady flow and picture B shows a steady flow. So next time when you go to Victoria Falls or to any waterfall that you are there, talk like an engineer. Don't say, oh, look at that flow, Shanshan. Or just say, like, look at that steady flow and look at that unsteady flow, and explain the properties that are there. That this flow, there is no change with time, and this flow, there are some changes with time. At least people, they will understand that you are an engineer. Okay. Last but not least, we need to talk about the dimension of flows, because we know that flow can be in 3 dimensions. We've got X, Y, and Z dimensions. That is if you are dealing with Cartesian coordinates. Then when you're dealing with spherical coordinates and cylindrical coordinates, we use different notations. So during your spare time, just try to find out what we use when we are dealing with cylindrical coordinates and when you are dealing with spherical coordinates. So for Cartesian coordinates, there's X, Y, and Z. In terms of velocity, we have got in X direction we have got U, in Y direction we've got V, and in Z direction we have got W. So we've got U, V, and W in Cartesian coordinates. So it's not every time that the flow will be flowing in all the 3 dimensions. For example, flow in a pipe, we can take it to be just flowing into 2 dimensions, which is R and Z. So R, which is due to the radius of the pipe, and Z due to the longitudinal direction that we have here. So this flow that we have will be mainly 2-dimensional flow that we have. So these diagrams that we have, also these graphs, they show what is known as velocity profile. So velocity profile, we know that the flow will be faster at the center of the pipe and slower as we reach the surfaces. So this is due to the first term that we talked about, which is known as non-slip condition, where we say that close to the surfaces the flow is equal to 0, and 0 at the surface itself, but away from the surface the flow reduces speed, also increases speed until we reach the maximum speed at the center of the pipe. So this profile that we have is known as the velocity profile. So we've got 0 velocity here, and velocity is increasing until we reach the maximum velocity at the center. So like this, now we can say that this flow is 2-dimensional because it's affected by the radius of the pipe and also by the length of the pipe that we have in this case. Okay, so what we are going to look at in this case, in this course, in summary, we will look at non-slip condition, steady flows, incompressible flow, 1 and maximum 2-dimensional flows. And in dynamics, we'll also look at forced flows, where we are going to use a pump and a turbine to solve some of our problems. So now when we are solving our problems, I've put a diagram here. Okay, I'll show you the diagram that I've put, where we are going to talk about how to solve the problem. But in this case, we still need this table to know the dimensions, how we are going to deal with the units that we need. So we've got about 7 fundamental or primary dimensions that we use in engineering, which is length, mass, time, temperature, current, light, amount of light, and amount of matter. Those are the 7 primary dimensions that we use. Then from these primary dimensions, we also have what is known as derived dimensions, where, for example, energy, pressure, volume, all those are derived dimensions, but we need to know these 7 primary dimensions that we use. So which means if you are answering any problem in fluid dynamics and you don't put any units to your answer will be considered wrong, because it's not mathematics. We deal with engineering. You need to know what quantities you are talking about. Okay. Then the other thing that we can look at is the prefix that we use for SI units. For example, iota, zeta, hexa, where we are talking about 10 to the power 24, which is iota. But in this course, I think we'll reach giga. So which means maybe giga newtons or something like that, or mega newtons or kilonewtons, a hectare. Those are things that we are going to work with. And for the smallest, we'll reach as far as nano. So just put in mind that when you hear nano, you know that it's 10 to the power minus 9. Okay. We'll use mainly SI units, so sometimes here and there we might need to convert SI units to English units or vice versa. So these are some of the conversions that we have, whereby we know that 1 foot is equal to 0.3048 meters, and 1 pound force is equal to this and what. But we'll stick mainly to SI units so that we don't complicate our lives, but you might just need to know some of these conversions. Okay. Let's conclude today's class by just knowing how we are going to solve the mathematical problems in engineering. So firstly, to solve any problem in engineering, we can use 2 methods that are there. Either you can work with an experiment, or you can use analytical analysis. So experiment, which means you need a laboratory where you have to do all the experiments to come up with a solution. And this one, it has proven to be very expensive and time consuming and often impractical, because there may be also a lot of errors that are there, and depending on the machine that you are using, you might come up with wrong answers sometimes. But though we should not neglect experimental approach, it's also a good way of coming up with solutions, because sometimes most of the experimental in most cases, experimental approach can replicate the actual situation that we have. Then the other thing that we have is analytical approach. This one is fast and inexpensive, but the only challenge that is there is the results that we get now are approximations, because we are mainly working with assumptions and coming up with ideal situations. So some of the definition that we're talking about, things like steady flow, incompressible flow, one-dimensional flow, all those are assumptions that we are going to use to solve our problems, because in this case we'll dwell much on analytical approach to do the actual solving problems using pen and paper. It's also important to use analytical approach, though it has got also these setbacks that we have, like we are using a lot of assumptions, approximations, so your answers might not be close to the ideal situation. Then there are also ways that have been put to solve engineering problems, the modern ways that we are using now, which is to deal with simulations, things like CFD. So those guys that are doing mechanical engineering in your 4th year will be together again in a course known as modeling and simulation, and I'll be taking you in CFD, which is computational fluid dynamics, where we'll solve engineering problems using computers. Though it has got also its own disadvantages, but it's way better than working with experiments and analytical approach. In that, it's a bit cheaper, and you can, depending on the power of the computer that you have, you can also replicate the actual situation that we have in the real world. Okay, so how are we going to solve the problems analytically? Number one, you need to find the physical problem that you want to solve, identify the important variables, make their assumptions, apply physical laws, differential equations, apply applicable solution technique, boundary conditions, then you get your solution. Basically, that's what we are going to be doing. So when you're doing our tutorials, I'll show you basically how we'll move from the physical problem until we reach the solution of the problem. So you can choose whether you want to go to use a complex model which is very accurate, or a simple model which might not be that accurate. So like what we're talking about, this is like a helicopter. You need to solve all the parameters for a helicopter. You can use this helicopter the way it is and still find your solution which is more accurate to solve your problem. Or you can use a simplified board where you just put a rotor in a simple board in the ground and solve your problem. You still get the answer that will be not so accurate, but can help you to solve the engineering problem that you are looking at. So basically, 7 steps that we need to follow: problem statement, schematic, which is to draw the diagram, assumptions and approximation, physical laws, the properties, then calculations is number 6. So which means if you want to get all your full marks in any given problem, you need to follow step 1 up to step number 7. If you just go straight to calculations, rest assured you won't get your full marks. Then the last part is to do the reasoning, verification and discussion of the answer. This is not mathematics. So if you get 500 newtons, you need to explain 500 newtons, what does it mean in terms of the problem that you are solving? Is it a large force? Is it a small force? Is it reasonable enough? Can it be verified? Can you discuss that answer that you have? Because most of you guys are engineers and they are working already, and some will be joining the industry. Your manager might not be a technical person. So if you tell them that the answer is 500 newtons, okay, so what does it mean? You need to explain to them 500 newtons, it means this and this and this. So relate your answer to the problem statement. So you need to get your answer and justify, put some reasons to the answer to make it more practical. Okay. So like what we're saying, you either choose the easy way or hard way to solve a problem. But at the end of the day, you still reach your solution. So for you to know which one is the easy way and which one is the harder way, or hard way and easy way, you need to constantly practice fluid mechanics problems. Like that booklet that I've given you, where there are problems and solutions. You need to constantly solve the problems. By doing so, you end up knowing which one is the easy way to use to solve a problem and which one is the harder way to solve a problem. Okay. So like what we're talking about, that this modern world, again, we are now using engineering software packages like ANSYS Fluent, ANSYS CFX, SolidWorks, Solid Edge, and all those things, the packages that we are using these days to solve problems. So mainly, if you are a modern day engineer, if you don't know computers, when people are asking for engineers to lift up their hands, please don't. If you don't know computers, the modern world of engineering will spit you out. You need to know computers, especially engineering software packages like SolidWorks, Solid Edge, ANSYS, the whole package if it's possible, but mainly Fluent and CFX and all those packages that are there, and other packages that I might not have explained. Yeah, and also programming programs like MATLAB, Python, C++, all those things. As an engineer of this modern or fourth engineering generation that we are in, you will need to know all those packages to be a complete engineer. Otherwise, the system will spit you out. Okay, so basically these are some of the basics that we need to know to progress in this course. So if you've got any question or any challenges, please just contact me on WhatsApp, or you can use my email izingapeta@yahoo.com. Then I'll be able to help you. Thank you very much for your attention. God bless you.